So chapter 16 is going to see us changing a little bit how we attack probability. It's not going to be what we've traditionally thought of with probability. You know, what's the likelihood of this event or that event? We're going to be dealing with different variables, and they're called random variables, as you can see by the title of the slide. And a lot of the same things that we covered in chapters 14 and 15 are going to play a role in this, but now we have to think about it just a little bit differently, and we will reintroduce an older but really important idea that we haven't seen in a little bit. So for this first lecture, we're just going to talk about some basics, some kind of basic vocab, what types of random variables that we're going to see, and then learn how to calculate what's called an expected value. And then we're going to go on with different stuff in different lectures. All right, so what is a random variable? Simply put, it's a random variable is the numeric outcome of a random event. You know, if you know, when we're talking about flipping a coin, we'll do an example later on. But if we know we are flipping a coin 10 times and keeping track of something, that whatever we're keeping track of is going to be the random variable. Now, how they denote random variables can get a little confusing sometimes. What we are keeping track of is usually represented with a capital variable, a capital letter, and then the possibility, the lowercase version of that is what the outcome could be, right? So in the case, if we see it written like that, which a lot of people find kind of confusing, it's the probability of some event X occurs X times, right? We're saying the same variable, but if we're looking at them, they're different variables, which is a little confusing at times. But if you look at it with a real world example, so let's say we flip a coin 10 times and keep track of the number of tails, for instance. What's the probability that you get 3 tails out of 10? Well, in this case, I'm going to scooch it up just a little here. In this case, the capital X is going to represent what we're keeping track of, which is the number of tails. The lowercase x is 3 because we're finding the probability that the number of tails, capital X, equals 3, lowercase x. So it might look like that. So the probability, so it's not a bad idea to jot the letters down, like capital X equals. What are we keeping track of? And then there's whatever number you're looking for is going to be what's in there. Okay. We're going to be dealing with 2 types of random variables as we proceed. And the first one is discrete. If we've got a random variable where you could list all the possible values that it could take, that's discrete. Take the example that we were just talking about. You're going to be flipping a coin 10 times and keeping track of the number of times it comes up heads. Well, it's going to be that number, that lowercase x, is going to equal 0, some whole number between 0 and 10. You're not going to get -7, you're not going to get 8.2, and you're not going to get 15 tails. And you're not going to get any of those because you just can't, right? So if you can list them, right, like we said there, x is going to equal anything between 0 and 10, whole numbers only. Right? Continuous is any random variable that could take any value within a range of values. So if I took my water bottle, which has a volume of 21 ounces, right, x could be anywhere between 0 and 21. Right? So don't necessarily, it could be 17.5, it could be 13.2, depends on how precise our measuring tool is. There could be many, volumes for my water bottle. It's certainly not going to be something you're going to easily list. I guess if you had time, you probably could, but you get the gist. Right? Usually, discrete variables tend to be counts, and continuous tend to be measurements. It's kind of like when we were talking about quantitative versus quantitative versus categorical variables, right? When we're talking about quantitative, those tend to be measurements, and when we talk about categorical, we tend to be counting them. And I think here's an example, and I apologize that the writing got cut off here. So the oversimplified insurance company offers a policy that pays $10,000 if you die, $5,000 if you're disabled. And the company anticipates having to pay $10,000 to 1 out of every 1,000 policies and 5,000 to every two out of every 1,000 policies. Well, from that, we can make what's called a probability model, right? Probability model is a collection of all outcomes and their probabilities. This is something we're going to want to start with in all these types of problems if it's not given to us. So if we're not given, oftentimes you are given the probability model, but if you're not, that's the first thing you need to be doing. And this is where some of the ideas from the previous chapters come into play, right? So we're looking at okay, we have 3 outcomes. We have 3 values that X could be. If X is the number of payouts, right? X could be death, disability, or neither. That's an option, right? That's an option. And the payout, X, could either equal 10,000, 5,000, or nothing. When you buy insurance, you hopefully never get any of your money back because that means nothing bad has happened to you. I'm going to pause in case there are any announcements. Doesn't sound like there are going to be any announcements, so I'll keep going. And then the likelihood of those events are kind of given over there, but there's one that you have to figure out, and it stems back to that idea that all the outcomes have to total up to 1. We know if there's one, the probability of paying out 10,000 is 1 out of 1,000. The probability of paying out disability, or 5,000, is 2 out of 1,000. That must mean they have a 997 out of 1,000 probability of never having to write a check for somebody, which is why insurance works, right? That's how it all works, right? So that's our probability model. All of these probabilities over here have to add up to 1, and they do, The probability of 1 1,000th plus 2 1,000ths plus 997 1,000ths adds up to 1,000 1,000ths, or 1. Right? So the last idea here is going to be the expected value, right? Or the mean of a random variable. The insurance company wants to have an idea as to how much they're going to have to pay out on average, right? That's the key idea with these. These are not necessarily going to be actual outcomes they're going to pay out. It's going to be what on average would they expect on every policy that they're going to have to pay. So we're going to put it in words first over here. How much could they expect to pay out on average given this probability model? Well, if they say they had 1,000 policies, right? They're going to write 1 $10,000 check, 2 $5,000 checks for a total of $10,000 or $20,000, right? We're going to divide that by 1,000, and on average, for every policy, if they were to average out all the amount of checks that they write out, if these are the outcomes and these are their probabilities, they're going to average on every policy $20 to pay out. No one is ever going to get a check for $20 from this company. They're either going to get a check for 10,000, 5,000, or 0. But if the company were to average them all out, it would be $20. And that's called the expected value of a discrete random variable. And how we find that is it's denoted 2 ways, either the Greek letter mu or capital E of X, expected value of X. And for those of you that don't know the Greek letters so well, we got the sum of the product of each outcome and its probability. Okay? So what that looks like in number sense here is what we did. We said, all right, there's a 1 out of 1,000 probability of writing a check for 10,000. There's a 2 out of 1,000 probability of writing a check for 5,000, and a 997 out of 1,000 probability of writing a check for nothing or never writing a check, right? Those are the only outcomes. We add those, we find those products, we add them together, and that will get us on average, right? If this company kept track of this for a while, they would say on average each policy would pay out $20, right? Which is going to help them say, well, I'm going to make, if I'm going to sell these policies, I have to collect more than $20 a policy. Elsewise, I'm probably not going to make money, or I'm not going to have money to pay for any claims that are made, right? So when they anticipate having to pay $20 for any policy, that will help them determine the cost. Okay. So that's expected value, or the mean of the random variable. Right? In the next lecture, we'll talk about that idea that oftentimes goes along with mean, and that's spread. And that should be a shorter lecture. We will get plenty of practice on this in class and in homework, so don't be afraid to give these a try, play around with this stuff when you have the opportunity. Please let me know if you have any questions regarding this, and I hope this helped.